after lecture 61, you are armed to basically look at most of the 230 space groups. However, I want to finish up here in this lecture with one of the missing things. You'll see lots of notation referring to glide planes, and so I just want to cover that. And then finish with some other, to make it complete, some other notation conventions, especially for the orthorhombic group, which has a lot of variance, more than any other system. And then we'll conclude there, and then finish summarizing everything and go through patterns from an international crystallographic database in the final lecture 63 of the crystallography. So let's just refresh what we had in 2D. So recall in 2D, a very common thing, for example, is when we had a mirror plane and we had another mirror plane, we would get a glide plane typically in the middle, and the notation we use was dashed line with two solid lines for mirror planes. These were actually mirror lines, as we used to call it once in a while, to make it more accurate. And you can see that one of the issues in 3D then is going to be, what do you do if I have a glide plane, which I'll now show like that with a tau in it, a slippage in that direction? Well, depending on when I'm projecting into 2D, which is how we show these things, so this is really about projection into 2D for tables and maps and things like that that can be displayed. We have to look at it from different perspectives, so I'll draw my little eye as I always do here, and there's kind of three possible projections when I'm looking. So if I'm looking at the side of a glide plane, then I show it as a dashed line. So when I'm looking this way, I show it that way. When I'm looking at it end on, I would show it as a glide plane coming out at me with a series of dots. And so that's how I look at it in that direction. And then if I'm looking at a 2D projection and I'm looking at the edge, of course, it's a mixture of the two. And so the convention is to draw it this way to show that you're at an angle, at some angle to it. It'll be defined by what system you're looking in and what projection you're looking at. But it's looking at along the diagonal, and so this is kind of that way. So as far as the convention goes, when I'm projecting into 2D, that's how we're gonna show this. There are additional conventions with glide planes because I need to show if I fix my base of my crystal. So this is a projection of some monoclinic base. So let's imagine it's a monoclinic 2D base. And now I want to show the sense of tau. See, in the other one I fixed the sense of tau and then showed you how you're looking at it when tau is in that direction. But how do I show the sense of tau if I'm looking at tau along this plane? Well, my choices can be tau going along B, if this is B and this is A, right? And so the way I would show that on a 2D diagram is a symbol like this, right? And by the way, that would be called a B glide. And you would see the symbol of B glide. Equivalently, just to show you and make you sure, I think you can already guess that if it was along this way, right? We draw a symbol like that, and that would be A glide. And A if it were necessary, would appear inside the notation. Finally, we have to make sure that if there is a ability to slip across the diagonal, but it's not going to be diagonal, by the way, that's coming up in a second. We draw this on a 2D diagram, and that's n-glide. So n-glide is for a diagonal glide, but of a whole thing. So diagonal and not diamond. To show you diamond, I have to switch crystal structures. So let's imagine an FCC face, in which case I have a lattice like this. And this is very common, of course, because this can be a slip direction in FCC when we talk about a real dislocation slip. But here we're just talking about the symmetry. And so if there's a pattern of motifs that moves along here, remember that this length is 1/2 A plus 1/2 B, that magnitude. And so recall that if we're going to have a tau, you'd have to have a motif kind of sitting here, and then it would appear, over here rotated, and then over here rotated back. And so the tau here would of course be 1/2 A plus 1/2 B. So this particular case, which you need a centered side in order to make this work, this would be a D glide. And so if you see a D, that's what that symbol refers to. So in general, other notation conventions are like, in general, for the sides, I know this doesn't make any sense, but the C is always treated as special. So if you're in another system, C is usually the unique axis. So for example, if it's a fourfold and the other are twofold, you don't have a problem. However, in the orthorhombic case, there are no unique cases really. There's only the links. And so what they do is they still keep to the rule that the magnitude of B is greater than the magnitude of A, just for the two sort of what we call in-plane components. But with orthorhombic, there's this case where, okay, we're also going to make C the shortest translation in the structure. And so again, that's a definition. Orthorhombic has many kinds of definitions that translate when needed into other lattices. So for example, you might have a centered lattice. So there's some sort of lattice symbol out front. I mean, that's true for a lot of the notations that you saw in the groups, right? In the space groups in the notation. But in the orthorhombic case, if the axis is parallel, whatever axis is parallel to A, that's parallel to A, and you put that over anything that is perpendicular to A. So remember, that's why we have 2 over M, because there's a twofold axis coming out, but the plane, a perpendicular horizontal plane causes us to do 2 over M, and that's why we had that notation, right? Then you have the same. Now, just to give you an example, and you'll see this in next lecture with some of the with the pictures of the groups projected into 2D, you'll see that you could have something that looks like this. For example. Well, since I have multiple axes and multiple perpendicular planes, what do I do? And here's how you do it. For orthorhombic, the convention is that the symmetries that aren't screws, so in other words, they're higher symmetric poles or axes, they dominate over the screw axes, which are less symmetric. And then in terms of the glide and mirror planes, the mirror plane dominates, and then a convention and pour D is last. And so that means that a mirror plane, right, would dominate over a glide, but then you have a hierarchy of glide planes in the notation. So if I were to apply those rules to here, this would result C2 over M, 2 over C, 2, 1 over M. And that would be the notation that we would use in that case. So the orthorhombic lattice system with all of the three-dimensional point groups gives so many variants that it really pushes the notation, especially the international notation. And so we had to develop these rules which spill over into some of the other lattices, but it gives you an idea where the notation comes from. And it shows you that the notation is created so that if you put those major elements in, the other ones should follow. So for example, in this case here, the idea is that, well, yeah, I didn't put a 2, 1 in there, but if I were to put in a 2 with a perpendicular mirror plane, you know, in this direction, and then I put a 2 in with a glide plane on C, and then I put a 2, 1 with a mirror plane perpendicular to it here, then all the other things will be generated anyway, and I don't need to put in more information. And so that's the kind of concept behind the international notation. So with that, we will go into our last lecture next time, where we will go over some of the two-dimensional projections of these 3D crystal structures, just to get you comfortable with that, and then you should have a complete handle on how to do these in the future.